Hello, welcome again. We are solving GATE 2017 Aerospace Engineering paper. Question number 36 is, in the figure below, water exits from a nozzle into atmospheric pressure of 101 kPa. If the exit velocity is V2 8 meter per second and the friction is neglected, the magnitude of the axial force on the plunge at location 1 required to keep the nozzle attached to the pipe is dash Newton. Round up to the nearest increase. So this is the plunge 1 and this is the exit velocity 8 meter per second and this is the diameter 4 centimeter and this is your 8 centimeter. So the mass flow rate through the nozzle is rho AB. Okay, so that is B is your 8 meter per second and A is 4 by 100 sorry 5 by 4 4 by 100 square. Okay, and rho is 1000. Okay, so mass flow rate is this quantity. So momentum thrust required is mass flow rate into velocity, so that is 80.384 Newton. So it will generate a momentum thrust equal to this, and at the exit the pressure is atmospheric. So it will also exert a force against atmosphere, and that force is 101 plus 101 sorry that atmospheric pressure into area. Okay, so that is 126.856 Newton. So here the total force which will be exerted here will will be exerted here. So we have to apply an opposite axial force to keep this flange attached to the pipe. So that is 207.24 Newton. So answer is 207.24. Next, question number 37. A football meant to be thrown at 100 km per hour in a sea level, rho is equal to 1.22 kilogram per meter cube, mu is equal to 1.78 10 to the minus 5 Newton second per meter square, is to be tested using a 1/4 scale model in the water tunnel. Rho is equal to 1000 kilogram per meter cube, mu is equal to 10 to the minus 3 Newton second per meter square. For dynamic similarity, the ratio of the model force to prototype force is, so for dynamic similarity that the Reynolds number of model and prototype should be same. So rho m Vm dm by mu m should be equal to rho p Vp dp by mu p. Okay, and the dynamic viscosity is given as 10 to the minus 3 for this model, and rho is 1000, and suppose Vm is velocity and dm by dp is 1 by 4. So rho p is 1.22 and bp is 100 kilometer per hour. Okay, and as dp by dm is 4, so we taking this as 4 and this as 1, and the kinematic viscosity of I 1.78 10 to the minus 5. So Vm is your 27.41 kilometer per hour. Okay, so that is the model velocity, and the ratio of force is given by the rho v m. Rho v a is the mass flow rate, and if we multiply it by g, then it will be a force. Okay, so for model the force will be rho m am vm square, and for prototype it will be rho p vp square ap, and am by ap is dm by dp whole square. Okay, so and Vm is your 27.41, we have calculated. Vp is given as 100, that is 1000, and that is 1.22. So putting these values and this as 1 and this as 4, putting these values, we get Fm by Mp is equal to 3.8 or 4. So answer is 4. Next, An aircraft model was tested in a low-speed wind tunnel, Renault number 2 into 10 to the 6, based on the wing mean course. The variation of the pitching moment coefficient (Cm) with angle of attack alpha for two elevator deflection delta E as reported during this is presented below. So this is Cm, this is 0.03 and for minus 10 degree delta E, and that is 0.02 for 0 degree, and this is angle alpha. Based on the result presented in the figure above, the value of elevator control power Cm delta E in radian will be in 3 decimal places. So elevator control power is Cm delta E equal to dCm by delta E. So we can see that with minus 10 degree change in angle, this Cm is increasing by 0.01. Okay, so converting this minus 10 into degrees, so minus 10 by 180 into pi, so that will be in degrees. So and this is your 0.01. So answer will be putting this value, answer will be 0.05729, because for 0.01 change the angle change is minus 10 degree, converting that into radian and then finding out the answer, that is minus 0.05729. Next, a pitot a pilot was flying a single engine propeller aircraft and maintaining a steady level flight at a lift coefficient CL is equal to zero point 0.5 at an altitude of 500 meters. Due to some emergency at the same altitude, so same altitude 500 meters, the pilot had to fully deploy the landing gear. If the pilot wants to maintain steady level flight at the same CL is equal to zero point 0.5 and at the same altitude, which of the following control sections should the pilot undertake? Option A, move the elevator up and decrease the throttle. Option B, move the elevator up and increase the throttle. Option C, move the elevator down and decrease the throttle. Option D, move the elevator down and increase the throttle. So answer is option B. Uh, when the elevators are deflected up, the lift on the tail is decreased. Okay, when the elevator are near the tail. Okay, so when they are deflected up, so the lift on the tail will decrease. Okay, because of that stagnation pressure, because of that restriction of air. Okay, and pulling the air down and nose up, and so tail will be pulled down and nose will be up. Okay, and and when we are taking landing, so actually what will do, we apply the landing gear, so it means uh, the tail so the nose is down and tail is up. So by moving the elevator up, we can balance these two. Okay, so by increasing the throttle, so that is the method to increase the to maintain the state level or the same level that we that was originally. Okay, and by now by incorporating by deploying landing gear, the drag has been increased. Okay, so to overcome drag, uh, it has to increase the total to uh, to maintain the same speed or same equilibrium. Okay. So answer is option B.